Here I have 2 points in the 2D plane, and to get between them I can move exactly 4 units across and then 3 units up. What's the distance between these 2 points? Well, a little bit of ancient Greek mathematics will tell us that the answer is obviously 5, right? There's surely no way it could be anything else. Well, let's take a look at what we're doing. We're saying that for 2 points, x1, y1, and x2, y2, the distance between them is square root of x1 minus x2 squared plus y1 minus y2 squared. This is an example of a distance function / metric. Specifically, it's the Euclidean distance metric, or more formally, the L2 metric. But it's not the only one. We can also have the L1 metric, where you add up the horizontal and vertical displacements like so, or we can have the L infinity metric, where the distance is the maximum of the individual vertical and horizontal displacements. The former is also called the Manhattan metric, because if you were driving in a place like Manhattan, where the roads are all neatly arranged in grids, this is the best way to measure distance, since you can only move straight across or up and down. You can't drive through buildings. The latter is called the Chebyshev distance sometimes, and is useful whenever you have a situation where movement along a diagonal is weighted, the same as a move directly up or across. The easiest example here is the king in chess. On each move it can move 1 square up, down or across, but also 1 square diagonally, even though a diagonal move covers a greater Euclidean distance. You may have noticed that we have L1, L2 and L infinity, but it's not immediately obvious how they're connected, or why I haven't mentioned any other L's. For example, does an L5 distance function even exist? Well, I'll tell you it does, and so do all numbers in between, because generally, when dealing with 2 points in a 2D space, the Ln distance between them is x1 minus x2 to the n plus y1 minus y2 to the n, all raised to the power of 1 over n. And technically we should be talking about the moduli of the differences so that we don't get negative distances. So our L5 distance formula would be this right here. Okay, cool, but when I defined L infinity, I just defined it to be the greater of the horizontal and vertical differences. And obviously I kind of had to do that to avoid raising things to the power of infinity and then infinitely rooting them or whatever, but it's not very satisfying that the pattern stops here, and it would be nice if we could show that these were the same two things. Well, here we go. To prove this, we're going to keep our x and y differences constant. Let's call them a and b. And, without loss of generality, let's say that a is greater than or equal to b. And for the sake of avoiding any weird shenanigans, let's say that a and b are non-zero real numbers. Then we can plug a and b into a general distance formula and consider what happens as n, our power here, approaches infinity. What we're going to do is rewrite our smaller number b in terms of a. We'll say that b equals a times 1 over k, where k is greater than or equal to 1. Then we can use our exponential laws and say that a product raised to a power is just the product of each element raised to said power. And here in our fraction, the numerator is 1 to the k, which is just 1, so we get that this part is equal to 1 over k to the n. We can then do a little factorization and pull out an a to the n to get this here, and then we can split our side into 2, getting the nth root of a to the n, and the nth root of 1 plus 1 over k to the n. The first part can just be simplified down to a, and since that means that it's now independent of n, we can take it outside of the limit. So it all comes down to this expression here, the square root of 1 plus 1 over k to the n, and its behaviour as n approaches infinity. Since earlier we defined k such that it is greater than or equal to 1, we can consider those two cases in turn. If k is 1, then as n approaches infinity, this expression stays constant at a whopping value of 2. So then, as n approaches infinity, the nth root of 2 gets smaller and smaller and approaches 1. In the other case, where k is greater than 1, it's even easier. As n increases, k to the n increases, and what's more, as n approaches infinity, so does k to the n. So 1 over k to the n approaches 0, and the whole expression approaches 1. At this point, the nth root of 1 is 1, actually, regardless of the value of n. So either way, we get this part here to equal 1, and so the entire expression is equal to a, which we defined as the greater of our two differences, which means that the two ways of defining L infinity are in fact one and the same. Now this entire time I've been referring to these horizontal and vertical differences / distances, and it seems like I've always been defining them using the Euclidean distance, even when I'm not working in Euclidean distance. But the thing is, if you have a purely horizontal or purely vertical distance, then it's the same length no matter which metric you use. If you consider 2 points, BA and CA, you get a straight horizontal line, and the ln distance of this, as it were, is going to be this right here. But the a's here cancel, and we end up just getting the absolute value of b minus a, regardless of how we're measuring it. Of course, identical reasoning can be used to show that this works for vertical distances as well. So it's certainly interesting to have more ways of measuring distance, and it's good to see the algebraic formulation for them, but it can be really difficult to visualize. To do that, we turn to the humble circle, which is of course the set of all points a given distance away from a single center point. We can pull up good old Desmos here and see what so-called circles look like when we change our definition of distance. This here is an L1 circle, and we can slowly watch it expand as we go up to L2, L3, and so on and so forth. This process is probably the closest you can get to squaring a circle. Now we have the visual intuition behind it, one final question remains. Are these ways of measuring distance special? Or could you just define distance however you want and call it a day? Now, believe it or not, the notion of distance has its own mathematical construct called a metric space. We won't really get into anything too deep here, but I will give the formal definition. A metric space is a set of elements x, along with a distance function d, such that the function d maps all possible pairs of elements of x to the reals, obeying the following three properties. Firstly, we have positivity, which means that all distances are non-negative, and the distance is 0 if and only if the 2 points are the same. Then we have symmetry, which just says that the distance from x to y is the same as the distance from y to x. And finally, and most interestingly I suppose, we have the triangle inequality, which says that the distance between x and z is less than or equal to the distance between x and y plus the distance between y and z, proving that these L metrics, which are called Minkowski distances, satisfy the three axioms is left as an exercise to the curious subscriber, but it does prove that this video wasn't just a load of rubbish. Thanks for watching.